So this is going to be n plus 1 times n factorial over n factorial. And this is going to be e to the n squared plus 2n plus 1 and e to the n squared. Okay. Now we have to note e to the n squared plus 2n plus 1. That's going to be e to the n squared times e to the 2n plus 1. Okay. Meanwhile, we can cancel these out. And I don't need the absolute value anymore. So we'll have n plus 1 times e to the n squared over e to the n squared, e to the 2n plus 1. And these will also cancel. Okay, so we're looking at n plus 1 over e to the 2n plus 1. Now, by the hierarchy of growth rates, who's growing faster?
The bottom.
The bottom. So this limit's going to give us 0. So our conclusion is that we converge by the root test.
Okay, the exponents is what confused me and how you separated them, but that makes more sense.
This is pre-calc. And the number one problem in this course is not calculus, it's pre-calc. Okay? A lot of people don't remember the rules for exponents.
Okay, thank you.
That was homework 13.3. And in case you didn't know, I've answered a lot of questions on homework 12 and homework 13 on the discussion board. So check those out if you haven't already. Okay. All right, can we get started then we're on the free response part of the second exam for fall 16. And we want to know if this series converged. And I did tell you guys, you will get a question like that. So everybody knows, right? Talk to me.
Yep.
Yes.
Okay, so we want to figure out what an is. That's easy. We're just going to repeat what's already there. 2 times 5 times 8, keep going until 3n minus 1 over 2 to the n times n factorial. Now, the an plus 1 term trips some people up because this is a running product. And that means multiply everybody together. And the next term will replace the n with n plus 1. So we'll still have 2 times 5 times 8 and the 3n plus 1. But we've got a new product, a new factor here that's going to be 3 times n plus 1 minus 1. Sorry. And the bottom, we replace the instances of n with n plus 1. Okay? Now, this last factor, what's it going to turn out to be? That's going to be 3n plus 3 minus 1, which is the same as 3n plus 2. Okay, so let's do our ratio test. So we'll have 2 times 5 times 8 dot 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 3n minus 1, 3n plus 2 over 2 times 5 times 8 dot 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 3n minus 1. And then we'll have 2 to the n plus 1, n plus 1 factorial, 2 to the n factorial. So we can see right away that all of these will be canceled. And we can write 2n plus 1 as 2 to the n times 2, and we can write n plus 1 factorial as n plus 1 times n factorial. And so the other things we can cancel are 2 to the n and n factorial. So what are we left with? Oh, I forgot the absolute values. Everybody is positive, so we don't need the absolute values anymore. We'll have 3n plus 2 on the top, 2 on the bottom, and n plus 1. Okay, where's that going to go in the limit? You got a polynomial degree 1 on the numerator, in the numerator and denominator. So the limit's going to give us the ratio of the leading coefficients, which is 3 over 2. So what's our conclusion?
Divergence?
This limit is greater than 1, and it diverges due to the ratio test. Okay? Questions on that one? Fall 16. Okay? All right, next one, you'll get a question like this as well. We've got a series and its partial sum. S sub n is the sum of all of this as you go to capital N, and that's going to be 9 minus 1 over n squared. So let's answer the questions. What is the limit as n goes to infinity of s sub n? Well, we're given an expression for it, so we'll just let capital N go to infinity. And where's this guy going?
0.
0. So that limit's going to be equal to 9. Okay, can we conclude that the series a sub n converges?
Yes.
Yes, if the sum of all those a sub n's is equal to 9, it definitely converges. Okay. Okay. It converges and the sum is equal to the limit of the nth partial sum as n goes to infinity. So that value is 9. So if the series converges, what do we say about the limit of a sub n? Anybody know?
Is it 0?
It's absolutely 0. Okay, that's what happens when you converge. Now, this limit being 0 doesn't guarantee convergence, but if you know that the series converges, this limit has to be 0. Now, what about s sub n?
Diverges.
That diverges by the test for divergence. Since the limit as n goes to infinity of s sub n is not equal to 0, diverges by the test for divergence. Okay. Okay, and let's see. What about, we've seen this before. We can write this series as n plus 1 a sub n plus sum n equal 1 to infinity 1. And we know that the first series is going to give us 9, but the second series is going to be 1 times infinity. So the sum is infinity. And so that compound series diverges. Okay. And this will also diverge by the test for divergence. Okay. Okay, that was it for fall 16. Now we're going to move on to the practice test that's on Canvas. Let me see where I put it. Here it is. Okay. All right, has everybody tried this yet?
Yes, I found this one
Yeah.
kind of tough.
Say that again, please.
I found this one kind of tougher than the other ones. I'm not sure why.
I'm sorry to hear that. There were a couple weird questions.
Yeah.
Okay, the first one is, which of these is bounded, divergent, and monotonic? Now, bounded means it's bounded from above and below, okay? Divergent means that it doesn't converge. Monotonic means it's either staying the same and getting bigger or staying the same and getting smaller, but not both. Okay, so look at this first one, -1 to the n. That's going to be -1, 1, -1, 1, -1, 1. And it is bounded, but it's not monotonic because it's going up and down. I can spell that. Okay, what about the next one? -1 to the n times n. Okay, that one is going to bounce between positive and negative numbers that are always getting bigger. So that one's not bounded and not monotonic. Okay, what about this guy? 0, 0, 0, 0, 0, 0, 0. It's bounded and it's monotonic, but it's not divergent. And what about this guy? This one is bounded. If you start at n equal 1, you'll have 1, 1/2, 1/3, 1/4, and so forth, okay? So this sequence, the limit as n goes to infinity of 1 over n is 0, okay? So this one converges. All right, so none of these choices work. The answer is that it's not possible for a sequence to be all of these things at the same time. Okay. Okay, how about the next one? Okay, this sequence a sub n is negative 2/3 to the 3n. And you can rewrite that as negative 2/3 cubed to the n. And that's going to give us negative 8/9 to the n. Okay, well, it's a sequence. So first thing you do is need to make sure that you're answering questions about sequences. If it says sequence, you use the theory for sequences, not for series. Okay, what do we know about a sequence when this ratio is less than 1? The limit as n goes to infinity will be what? Anybody know if this ratio is less than 1?
0?
Yes, it goes to 0. So this one converges to 0. Okay, you can prove that to yourself pretty easily. If you can't remember, when n is equal to 1, we have negative 8/9. When n is equal to 2, we'll have 64/81. When n is equal to 3, this wasn't a good example. I'll give you the decimal form. .62. I'll do one more so you can see the trend. The absolute values here, okay? It's getting smaller. So if this ratio is less than 1, when you raise it to a higher power, it gets smaller, and the general trend is that it's going to 0. No, you can have geometric sequences, yes. Geometric sequences, if the absolute value of the ratio is less than 1, it'll converge to 0. Okay? Only if the ratio absolute value is less than 1. Okay? You see that? Okay. Yeah, this is the sequence. We're not doing a test. There's no test here. We just took the limit. Where's the test? I don't see any test here. I'm just showing you that these numbers get smaller in absolute value as n increases. Do you see that? Oh, well, when we're doing a series, when we're summing a series, if the absolute value of r is less than 1, we can sum it. Okay? But for sequences, if the absolute value is less than 1, the limit will be 0. But we don't call that a test. Okay? But yeah, if the absolute value of r is less than 1, the sequence will converge to 0. If the absolute value of r is less than 1, you can sum the series. Okay? Okay. Now, I didn't like this one because he started at n equals 0. But here he says the sequence of partial sums of a sequence a sub n has this formula: s sub n is 1 over n factorial. And we want to find a2 plus a3 plus a4. Okay. So s sub 0 is given by the formula. That'll be 1 over 0 factorial, which is 1. S sub 1, and that's just a sub 0. S sub 1 is 1 over 1 factorial. That's also 1. That's a sub 0 plus a sub 1. S sub 2 is 1 over 2 factorial, which is 1/2. A0 plus a1 plus a2. S sub 3, and so forth. So let's go to S sub 4. That's going to be a1 plus a2 plus a3 plus a4. And the formula for that one, we'll just stick in 4 for n factorial. That's 1 over 24. Okay, we just want a2 plus a3. Oh, that's also a0 is included here. So if we want a2 plus a3 plus a4, that's going to be s sub 4 minus s sub 1. Okay, do you see that? We're subtracting these two. So that's going to be 1 over 24 minus 24 over 24. And the correct answer here should be negative 23 over 24. Okay, I think this one was listed as the correct answer for the first few days. That's,
Yeah, it was.
yeah, Dr. Manley made a boo-boo. This is the correct answer. He doesn't make them very often. Okay, number 4, how many of the following series diverge by the test for divergence? Okay, that means we get a non-zero value. This first one is going to give us 0, so that's not it. Second one, I think you can tell right away from the hierarchy of growth rates. The denominator is growing faster. This also gives us 0. What about this guy?
Alternate, so diverges.
It's going to be 1, negative 1, 1, negative 1. This one diverges. Okay, for this one, we know we can do squeeze theorem. Sign is always trapped between negative 1 and 1. Divide all 3 pieces of this 3-way inequality by log of n, and you can take the limit of these two, and that's going to 0. Likewise for this guy. I think by the squeeze theorem, this limit also goes to 0. Okay, so the answer here was that only one of them diverged. Okay. Okay, which of these can we find using techniques in class? The sum. Okay, we only showed you how to find the sum for 2 types of series. Does anybody want to tell me what they are?
Geometric and
Geometric and
telescoping.
telescoping.
Yeah, geometric and telescope only. All right, that's not a geometric or a telescope. That's not a geometric or a telescope. But this guy is geometric. Okay. So this is the only one. And we're not asked to find the sum, but that's the answer. Okay, next one. What kind of a series is this?
Telescope.
This is a telescope. And we've got 3 terms. So what we're going to do, we need each 2 terms have to have alternating signs. So we're going to rewrite the middle term as arctan. We're going to split that up into minus arctan n minus arctan n plus arctan n plus 1. And then we're going to put the divider between the first 2 and the last 2 terms. And then I'll do that up here, okay? And we're starting with n equals 0. It's important to start at the right index. So n equals 0, we have 1 minus arctan 0. And then we'll have arctan 0 plus arctan negative 1. And then arctan 2 minus arctan 1, arctan 1. Oh, this is also a negative sign, negative plus arctan 0, dot, 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 all the way down to arctan n plus 1 minus arctan n minus arctan n plus arctan n plus n minus 1, sorry, minus 1. All right, if you can read my checking scratch. We're going to cross out the terms. I thought for sequence, we just take the limit, we couldn't do a test. Oh. Will we get the same if we don't divide it like that? No, you have to do it like this, okay? You need an even number of terms in each section. If you have 3 terms, you have to turn it into 4. And you have to alternate signs, otherwise you won't get cancellation, okay? Got it?
Yes, thank you.
All right. So all these diagonals will go away. We'll be left with this and this. And all these diagonals will go away. We'll be left with this and this. Okay, so we're looking at the arctan. I'm going to call it tangent arctan of 1. Oh, what's left? Arctan of 0 with a negative sign in front of it, minus the arctan of 0, plus the arctan of n plus 1 plus the arctangent of n plus 1. Okay, these are both 0. So what are these going to give you? Remember the arctangent of infinity?
Pi over 2.
Pi over 2, right. Wait a minute, I crossed this one out the wrong way. I'm sorry. Nobody said anything. This one is crossed out the wrong way. We're left with this one. And this one, not that one. So we'll have arctan n plus 1 minus arctan n. Let me do that over again because I can't see what I've done here. Okay, is that consistent with our series? Yes. Okay. Okay, and then we go down. Okay, there we go. Okay, now we're going to cross out these diagonals. And we're going to cross out these diagonals. And what are we left with? This one, this one, this one, and this one. And this one goes to 0, so we don't need to consider it. Okay, so we'll have the limit as n goes to infinity. What's left? The arctangent of n plus 1 minus the arctangent of n plus the arctangent of -1. Now these are both going to pi over 2, but we cross them out, okay? Because we're subtracting here. So that minus that goes to 0. Now, does anybody remember the arctangent of -1? Anyone?
Negative pi over
Negative pi over 4, and that's your answer. It's not complicated. I just tried to do it too quickly. Okay? This is really not that complicated. I just tried to do it that quickly. So don't be intimidated by that. That was my mistake. Okay. All right, what's next? Okay, p-test and generalized p-test. Do you remember from your lecture notes when we discussed these?
The integral test.
That's right. Those are from the integral test. Okay, and now for number 8, we want to know which of these series converges by the generalized p-test. Okay, we know that this guy is divergent. How about this one? A lot of people are tripped up by this, e to the 2 log of n. You can write that as to the e to the log of n squared. What's e to the log of n?
N.
N. So that's n squared. So does 1 over n squared diverge?
No.
No. So it's not that one. Okay, what about this one? Okay, he didn't say anything about generalized p-test for the log of n squared. Okay. So that's not it either. Which one do you want me to explain, this one or this one? Okay, we can write e to the 2 log n as e to the log of n squared. Got it?
Yeah.
And e and log, those are inverses of each other. They undo each other. So if you raise e to the log of n, that just gives you n. And that quantity is squared.
Okay. And that doesn't. And that diverges, right?
It converges, no?
Oh, we're looking for, I'm sorry. We're looking for
Yeah.
Yeah, we are looking for convergence. So I shouldn't have crossed that out. That's it. We are looking for convergence. That's the answer. You know what? He shouldn't have said generalized. He should have said p-test or generalized p-test. Okay, he should have said or here. Okay, he doesn't write things properly all the time. I'm sorry about that.
Wait, and sorry, the bottom one, the 1 over n ln n squared, and that diverges?
We didn't finish that one yet.
Oh,
Okay, because there's more. These two are both correct as well. Okay, remember, if n equal 1 and ln n to the p greater than 1, we converge, right?
Yeah.
Okay, what about this guy?
converges.
Right, because you can write this as n equal 2 to infinity, 1 over n squared log n to the negative 3. And if this guy is greater than 1, it's going to converge. So this also converges. Okay. Yeah, he should have written p-test or generalized p-test. He didn't state this question properly. So don't get hung up over that, okay? Now I'm getting a lot of questions about why he wants you to use this series or not. He was really trying to make it easier for you somehow, but it didn't come across. Okay, what about this one? Okay, we can, what do we want to do here? Anybody?
Limit comparison.
Well, we can do limit comparison. This series diverges, so when we do limit comparison, arc sine 1 over n over 1 over n. What's that going to give us in the limit? If we go to infinity, arc sine of 0 will give us 0. 1 over n will give us 0. We have to call L'Hopital. Okay. Does anybody remember the derivative of arc sine?
One over 1 plus n squared.
1 over the square root of 1 minus 1 over n squared times the derivative of what's inside, which is negative 1 over n squared. And here we have negative 1 over n squared. And these will cancel. And n is going to infinity. This guy goes to 0. We get 1, which is finite. So if the limit of an over bn as n goes to infinity is finite, that tells us that an and bn have similar growth rates. So if bn diverges, that tells us that an does what?
Diverges also.
Right, bn diverges, that means an diverges also. So this is correct. Okay, does it diverge by the test for divergence? No, it'll give us a 0. So for this one, if we take the limit as n goes to infinity of arc sine 1 over n, that'll give us 0, so that's not right. Okay, integral test. All right, that means we have to integrate that guy. I'm gonna need another piece of paper to integrate that guy. Okay, what is the integral test? Positive, continuous decreasing. And you do need to know the conditions. It has to be positive, continuous, and decreasing. And then we will replace our series with the indefinite integral. And we'll put in x to make it continuous. And whatever the integral does, the series will also do, okay? Okay, and arc sine 1 over n is decreasing. 1 over n is going closer to 0, and arc sine will also go closer to 0. Okay, so we need to integrate this by parts. Remember, if we have an inverse function, it's going to go under the d column, and I will just have a 1. When we take the derivative of, this is arc sine, isn't it? We'll have 1 over the square root of 1 minus 1 over x squared times 1 over x squared with a negative sign in front of it. And here we'll have x. Okay. Okay, so that's going to give us x arc sine 1 over x minus a negative. We'll have plus the integral of x over the square root of 1 minus 1 over x squared times negative 1 over x squared dx. Okay. Now I've got to make this prettier. So what I'm going to do is bring this radical. First of all, I'm going to cancel one of these x's. I'll use ditto mark there. So we'll have 1 over x square root of 1 minus 1 over x squared dx. Okay. And now I don't want to blow your minds, but if x is greater than 0, x is going to be the same as the square root of x squared, right? Everybody agree with that? Anybody agree with that? Anyone?
I
Yes.
agree with that.
Okay. So I can write that integral as 1 over x squared times 1 minus 1 over x squared. Okay, and when I distribute, we'll have the square root of x squared minus 1. Okay. Okay, does anybody know what that integral is?
Secant, right?
Arcsecant, yeah.
Also, whatever happened to the negative sign in front of the 1 over x squared on the top
Okay,
there?
I have a negative here and I have a negative here, right?
Yeah. Oh, okay.
So I should have made this positive. Should have made that positive. Okay, there we go. All right, now we have to take this from 1 to infinity. So we'll take the limit as n goes to infinity. Infinity times the arc sine of 0 plus the arc secant of infinity minus arc sine 1 plus arc secant 1. Okay, anybody know what arc secant looks like? Arc sine of 0 is 0, so that goes away. Arc secant of infinity, that guy's going to diverge, okay? That guy makes us diverge. So this integral diverges by the integral test. Okay, I don't think so because we have a negative times a negative, so it should be positive here. Okay. So this one diverges by the integral test. All right, and diverges by the p-test. Now, p-test doesn't apply here. We didn't do ratio test here. I don't think you're going to see anything if you do ratio test.
Well, couldn't you just know because it says it diverges because it yields 1 when that would be inconclusive?
You don't know if this is true or not. You have to test it. What I'm saying is it does yield 1. They're going to be essentially the same. But ratio test yielding 1 does not tell us that the series diverge. So this is a false statement. Okay. Got it? I certainly hope not. No, he's a little mean sometimes on his questions in the practice test. But I'm not the guy who gets to write them. I don't get to write the tests either. So I'm sorry. So I want you to know I don't write the lecture content. I don't write the tests. I don't write the practice tests. Well, I did make one for you last semester or last time, and I think it was a little bit easier than his. I made the one marked A, he made the one marked B, but I didn't do it this time because I didn't want to mislead anybody. He knows what he wants to put on the exam and I don't. So how many of these are true for sequences that are greater than or equal to 0 and defined for n greater than 1? Any bn that will work, that is to show us what we're looking for, converging or diverging, for the limit comparison test will work for the direct comparison test. Do you agree with that?
No.
No, you have to be more prudent about what you pick. Okay, what about this? If an is less than bn, then the series an converges.
Not necessarily, right? Because doesn't BN have to
No, it depends on what bn does.
Right.
Okay. Same thing here. We don't know if an is going to diverge. It depends on what bn does.
Can you explain the first one again, please?
Yeah, he's saying that anything that works for limit comparison will also work for direct comparison. That's not necessarily true.
Oh yeah, because sometimes we need one bigger than the other or smaller.
Yeah, sometimes we have to make adjustments. Sometimes we need a BN that converges more slowly. Sometimes we need a BN that diverges more quickly. So you can't make that generalization. And the fourth one is also true. Also false, sorry. None of these are true. Okay, how about this one? Limit comparison. I had a bunch of people asking me, why did he use this BN? Okay, and that's not part of the question. All you have to do for this question is figure out which of these statements is true. Okay, now what's going to happen if you use this BN?
It will yield 1.
No, it doesn't. Let's see, limit comparison. First of all, what do we know about BN? Using the generalized p-test, is this going to converge or diverge?
Diverge.
Wait, what was part 4 of the question? It's not true. Sometimes you have to adjust your BN, okay? Sometimes you have to find something that converges but more slowly. Sometimes you have to find something that diverges but more rapidly, okay? We cannot make these two generalizations, the first and the fourth. Is that good? None of them work. None of these are true. Okay. Is that good? Okay. Okay, so let's see what happens if we do limit comparison with BN. Is this series going to converge or diverge?
Diverge.
This one diverges. Yeah, we have to have n greater than 1 or the power on log n greater than 1. Okay. So let's do limit comparison for this series. 1 over sine squared of n and log n. 1 over n log n. Okay, what does that give us? Okay, now we know that sine squared of n is between 0 and 1. Okay. Right?
Yes.
So if we're dividing by that, this goes to infinity, doesn't it? Okay, so we need another bn. This is going to infinity. This is going to oscillate between 0 and 1, and this is 1. So we're oscillating between infinity and 1. So this isn't going to work. So we need another bn. Okay, we want to show something diverges. We want to compare it to something that diverges more slowly. Okay, one that diverges more slowly. Okay, and that basically means one that has a larger denominator. Okay, and in fact, he gave us a larger denominator. These are our only 4 choices, so we're going to go ahead and use this one that he gave us. I had a couple questions on the discussion board. Why are we using this? That's not what the question is asking. He's trying to make it easy on you by giving you a b sub n. So we're going to go ahead and use the one that he gave us. We already know that this one will not work. Okay. So we're going to do limit comparison again. And we have 1 over sine squared of n log n, and that's going to be 1 over n log n log n. I think he's just having fun here, okay? So we can cross out this guy and this guy. And what are we going to be left with? The log of n over sine squared n. Okay. Now, where is this going to go? Now, you know, this is going to be going between 0 and 1, but where's this guy going?
Infinity.
Infinity. Okay, it's going to go to infinity, and then we're trapped between 0 and 1. Okay. So this one diverges, but it's definitely diverging because it's oscillating between values that approach infinity. Okay. So that's your answer. Okay. Oh, I actually forgot. Did I forget something? No, that's it. Okay. Okay, what about 12? Any series with only positive terms that converges. What's the answer here? Why does it yield infinity? It diverges. Okay. Yeah, infinity over 0 is still infinity. Infinity over 1 is still infinity. So any possible value in the denominator will still give you infinity. Do you see that? I hope you see
Yeah.
that. Okay. Yeah, these are kind of tough. I don't know why he's doing this to you. I'm not sure he realized how difficult it would be. Okay, number 12. If a series has only positive terms, but it converges, what does that tell us? Anybody?
Absolute.
Yes, that's absolute convergence. If it's only positive and it converges, that's absolute convergence. Okay, we're coming down to the finish line.
If it said negative and positive, would it be like absolute or conditional?
If it's negative and positive, it's either conditional or absolute.
Okay, thank you.
Okay, which of these will work for alternating series tests? Okay, here he's saying an is 0 when n is odd, and an is even is 2 over n when n is even. Can we use 0 terms in alternating series tests? Anybody remember? What does alternating series test? What are the conditions for alternating series tests?
Positive?
Decreasing, and the limit has to be 0.
Greater than or equal to 0 and decrease. Okay. You'll need to know all these conditions. Okay, we're greater than or equal to 0, but are we decreasing?
I think we're going like back and forward between 0 and a number, 0 and a number, like that, right?
Yeah, we're going back and forth between 0 and a number that's positive. So we're not always decreasing. And that means that AST does not apply. Okay, so that's not it. All right, what about this one? Okay, we do have an alternating here, but sine
It's oscillating.
is oscillating between 1 and -1. Also not strictly decreasing. Okay, what about this guy? Okay. By the hierarchy of growth rates, who's growing faster, the numerator or the denominator?
The denominator.
Oh,
The
it's
denominator is growing faster, so always positive. Decreasing, yes. And the limit as n goes to infinity of n factorial over n to the n goes to 0. So this is an answer. Okay, what about this? I can rewrite that. I can rewrite that as -1 to the n times 1 minus 1 over n to the n. Okay, anybody recognize this guy? As the limit is going to infinity. We have a minus sign there, so that's not going to be positive. It's not going to be e, it's going to be 1 over e, right?
Yeah.
Okay, so we're bouncing back and forth between 1 over e and -1 over e. Okay, so that's not decreasing.
Wouldn't pulling the -1 out make it 1 plus 1 over n? Or am I wrong?
Oh, yes, you're correct, actually. I'm sorry about that. It's still bouncing back and forth. Okay, thank you for correcting me. Okay, what about this one? Is sine pi over 2 plus n pi an alternator?
Yes.
Yes, it is. This is the same as -1 to the n, right? So we have -1 to the n over n to a very small number. But we still have the fact that 1 over n to the 0.0001 is positive. It's decreasing. And if we take the limit, we'll get 0. So this one also works with AST.
For the first one, what would we have to change to make it like stop oscillating? I mean, the second one, sign.
The second one,
What would we change in sign to make it stop oscillating?
use another function.
Oh yeah, but like, I mean, what would that function have? Like, for example.
Well, you could replace this with 1 or n to the 1/2, but not a sine or a cosine. Okay, not a trig function. Okay.
Okay.
And the reason why the -1 minus 1 over n to the n, it doesn't work because it's not decreasing. It's alternating but not decreasing. Is that why it doesn't work?
And minus, yeah, it's decreasing and increasing and decreasing and increasing. Okay? And also the limit is not ever going to go to 0.
True. Okay, thank you.
All right, how about this one? We want to use the root test, which is, we're going to take the absolute value of arctangent n to the n squared over n to the n and elevate it to the power 1 over n. Okay. Okay, so n squared to the 1 over n, this is always positive as n goes to infinity, so is the denominator. We'll end up with the limit as n goes to infinity, arctangent of n squared over n is n, and n to the n over n is just n. Okay. Okay, who remembers what is the arctangent of n as n goes to infinity?
Pi
Pi over 2. So we'll have pi over 2 to the n over n. Okay, now where's this limit going to go? When n is in the exponential position, that beats a polynomial, right? In the hierarchy of growth rates.
Yeah.
So the numerator is growing faster than the top. That limit is infinity. So the series diverges. Okay. All right, how about this one? Okay, if you see factorials, what test do you want to use?
Ratio.
Exactly, ratio. So let's do ratio test. So we're going to have 3n plus 1, n plus 1 factorial over 3 to the n factorial times n plus 1 to the n plus 1 n to the n. Why am I allowed to put the limit in the degree n for the last one? I'm sorry, is there an issue here, here, or here? Where's the issue? Here? Okay, because n squared over n is equal to n. Do you agree with that? Okay, and we have n to the n divided by n. That's going to give us just plain n. So are you okay with this? Okay, now what happens to arctangent? This is arctangent. And as n goes to infinity, arctangent goes to pi over 2. So I made that a pi over 2 to the n. Okay? Now, when n is in the exponential position, remember in the hierarchy of growth rates, n to the p doesn't grow as fast as a to the n. So the exponential is growing faster than the polynomial, so we get infinity in this limit. Okay?
That's true.
You got it? Okay. All right, now let's go back to this. 3 to the n plus 1 over 3 to the n is going to give us 3. This is going to be n plus 1 times n factorial. And this one is a pain in the butt. I'm going to drop the absolute value bars. So we'll have 3 times n plus 1. And then we'll have n over n plus 1 to the n. And we'll have a leftover n plus 1. Now, does anybody remember where this is going to go? I've done this at least a half dozen times. As n goes to infinity. This goes to 1 over e, right? So we're going to have the limit as n goes to infinity. These guys will cancel. 3 over e. Okay, is 3 over e greater than 1 or less than 1? E is around 2.7, so this is greater than 1, which means we diverge.
Always recognize the other form, the 1 plus a over x. Is there a way to turn that n over n plus 1
Yeah,
to?
I've done it a dozen times. We can rewrite n over n plus 1 to the n. I can divide the numerator and denominator by n to write this. And I can rewrite that as 1 plus 1 over n to the negative 1. Okay, now it's in that form that you recognize. Okay.
Oh yeah, thank you.
Okay. All right, how about the next one, ratio test? I answered this one on the discussion board. Is it okay if I direct you guys to the discussion board for this one?
Yeah.
Okay. And if you have questions about the way I did it, please ask. Okay, what about this one? What do we have here?
Geometric.
This is a geometric series, and we can write it 5 to the n times 5 over 6 to the n times 6 to the negative 1. And that means you can bring it upstairs. So we'll have 5 over 6 to the n times 30. Okay. So we're looking at 30 times the sum from n equal 2 to infinity, 5 over 6 to the n. Okay, this ratio 5 over 6, its absolute value is less than 1. So we know it's going to converge, and we can find the sum. The sum is going to be 30 times the first term over 1 minus the ratio. And the first term depends on the starting index, which is 2. Okay. So that's going to be 30 times 5 over 6 squared over 1 minus 5 over 6. And that's going to be 30 times 25 over 36 over 1 over 6, right? And that's going to be 30 over 1 times 25 over 36 times 6 over 1. I've got a string mark there. Okay, so we'll have a 30 times 25 over 6, and this will give us a 5. So that gives us 125. You're definitely going to get one like that. Okay, how about this? Which ones convert? What kind of a test are we going to do for most of these?
Limit comparison.
Right, if you have sine or tangent and a function of n other than n itself, you're going to do limit comparison test. And our bn is going to be the argument to the sine function, including anything that's left over. And we know that this one is going to converge. So we'll do the limit as n goes to infinity, sine of 1 over n over n over 1 over n over n, and these will cancel. So we'll have the sine of 1 over n over 1 over n. Okay, and here's where I make a variable substitution. Let t be 1 over n. As n goes to infinity, t is going to 0. So we'll have the limit as t goes to 0 sine t over t. Do you remember what that limit is?
1.
1. Okay, which is finite. So that tells us what bn does. An does it too. So do we converge or diverge? Bn converges The limit is finite, so this one converges. I think I need another piece of paper for the next one. Okay, so if we have sine 1 over n squared, what's bn going to be?
1 over n squared.
Right, 1 over n squared, which converges. So we do limit comparison. Sine 1 over n squared over 1 over n squared. We're going to let t be 1 over n squared. As n goes to infinity, t goes to 0. We're going to get the same thing. Sine t over t is 1. Okay, that's finite. Bn converges, so an also converge. So this one is also correct. Okay, what about this one? 1 over sine n squared. What are we going to pick for bn? Okay. Okay, and this one converges. So if we do the limit comparison test, we'll have n squared over the sine of n squared. Okay, now you know this is going to oscillate, but where's the numerator going? It's going to infinity, right? But it's divergent. It's an oscillating infinity, actually. We could try a bn is 1 over n to the 1.5. Okay, that will give us the limit as n goes to infinity, n to the 1. Yeah, that's going to go to infinity too. So that one doesn't work. Okay, what about this one? Okay, we're not told what test to use. We do know that as n goes to infinity, 1 over n goes to 0, and the cosine of 1 over n will go to 1. So cosine 1 over n is less than or equal to 1. Dividing both sides by n squared, that tells us that an is less than or equal to bn. Bn converges, so by direct comparison, an converges. So that one also converges. And how are we going to do tangent? What's the test we use for tangent when we have a function of n other than n itself?
Limit comparison.
Limit comparison. And we're going to let bn be 1 over n squared. Okay, it's just going to be exactly like this because tangent is sine over cosine. The cosines will go to 1, but the tangent will do what sine does. So this one will also converge. Do you want to see that in details? Anybody? Yes, okay. Limit as n goes to infinity, tangent 1 over n squared over 1 over n squared. We're going to let t be 1 over n squared. As n goes to infinity, t goes to 0. So we'll have the limit as t goes to 0, tangent t over t, which is sine t over t cosine t. Okay, and we have to use L'Hopital here. So we'll have cosine t over cosine t minus t sine t. Okay, and this guy goes to 0, but these guys will go to 1, and that's finite. Since this limit is finite, and B sub n converges, this will also converge by LCT. Okay. Okay, this one is definitely not going to be on the exam. That's why I crossed it out. But what we're saying is we start by throwing a ball up from the ground at a height of 5 meters, and then it's going to bounce. And when it bounces again, it's going to drop to 1/3 of the previous height. And we want to know how much distance have we covered, okay? So we're going to start with 5, and then each of these is the same distance. We'll multiply it by 2. And then we'll start with our initial bounce. The next bounce is going to be 1/3 as much. The next bounce is going to be 1/3 times 1/3. The next bounce is going to be 1/3 times 1/3 times 1/3. So this is equal to 10 times sum n equals 0 to infinity 1/3 to the n. And that's a geometric series, right? And 1/3 is less than 1. So the sum is going to be 10 times 1/3 to the 0 over 1 minus 1/3. And that's going to be 10 over 2/3, which is 15. All right, last one. I'm down to 12 people. Which test can you show absolute convergence with?
Ratio and root.
Actually, all of them, you're just going to plug in, make sure your series is positive. These will all work. This one doesn't work because we need to have an alternator. And this one doesn't work because it only tells us if something diverges. So test for divergence says nothing about convergence. Okay, that was it. Questions? Anything you want to see again? Additional questions? None? Did I put you all to sleep?
No.
Okay, I didn't get a lot of questions this time.
We work through the number 16 one just to see it work through, maybe, even though you did it on the discussion board.
Okay, this one was actually pretty simple.
Okay.
Okay, so we want to do ratio tests. So we'll have the limit as n goes to infinity, 2 times n plus 1 factorial over 2n factorial. And then we'll have n plus 1 to the 2 times n plus 1 and n to the 2n. Okay, now this quantity is 2n plus 2 factorial, okay, if you just distribute the 2. So we'll have the limit as n goes to infinity. Everybody's positive. I'm going to drop the absolute values. We'll have 2n plus 2 times 2n plus 1 times 2n factorial over 2n factorial. And then we're going to have n to the 2n, and downstairs we're going to have n plus 1, and distributing we'll have 2n plus 2. Okay. Now these two will cancel, and then we can work on this guy. So that's going to be the limit as n goes to infinity, 2n plus 2, 2n plus 1, n to the 2n, and downstairs we'll have n plus 1 to the 2n times n plus 1 squared. So we can rearrange the furniture. We'll have 2n plus 2, I missed 2n plus 1, over n plus 1, n plus 1, and then we'll have n over n plus 1 to the n squared. Okay, now this part, as n goes to infinity, where is this part going? We have polynomial degree 2 in the numerator, polynomial degree 2 in the denominator, and the limit is going to be 4. Okay, do you remember what this guy is?
1 over E.
Okay, that's 1 over E, but it's squared. So that's going to give us 4 over E squared. All right, is that
Thank you.
greater than or less than 1?
Less than.
We converge. Cool. Other questions? No other questions? Okay, I'll see you guys tomorrow at 3. If you have questions, please post them on the discussion board. Wait, there's, how many of you are still here? 9? Okay, some people didn't get my email. If you are doing the root test and you have a polynomial to the 1 over n, do you remember what that limit is?
1.
1. Okay, and if you have a function that is less degree than a polynomial, like the log of n to the p, what do you think that's going to give you?
1.
That's also going to be 1. Okay, what about this guy? Anybody want to make a prediction there? Okay, this one, it's impossible to see, but this one is growing faster than polynomials or exponentials. So that one's going to give you infinity.
Oh, okay.
Okay, just in case you see this on the exam, because we didn't cover it in the lecture. I did send this out in a Canvas message, but I just want to make sure you guys have these in your memory palace, just in case you need them. And we can't even prove this until a 4,000 level course, so I don't think it's fair. But just in case, you'll have it just in case, okay? All right, then I'll see you tomorrow or on the board, and if not, good luck. I will be reading for you, okay?
Thank you. Have a good day.
Thank you.